Okay, we're going to continue on in section 6.1, and we're going to start with degree of a vertex. The degree of a vertex is the number of edges that you find at that vertex. Now notice a loop counts as a degree of 2 for the vertex, and we'll look at an example of that next. So the degree of the vertex, there are 1, 2, 3, 4, 5 edges coming out of A, so the degree of A is 5. B, there's 1, 2, 3 edges, so the degree of B is 3. C is 2, D is 2. Now E, there's 1, 2, 3, 4. We counted that loop twice, so the degree of E is 4. Now we have a theorem that goes along with the degree. And this theorem states that if you take the degrees that we just found and you add them all together, that it's equal to 2 times the number of edges in the graph. And the reason why this is true is because if you look at an edge has 2 endpoints, so an edge is counted twice, once at each endpoint. So we want to verify this theorem. Well, first of all, our D is equal to 16, because if you add all the degrees up, we get 16. And our number of edges, if you count the edges in this graph, 1, 2, 3, 4, 5, 6, 7, and 8, have 8 edges. According to the theorem, 16 should be equal to 8 times 2, or 2 times 8, and that is true. So we have verified the theorem for this case. Next thing we're going to look at is paths. Paths are a way to get from one vertex to any other vertex. It's just like playing dot to dot. So you have to use adjacent vertices to play dot to dot because they have to be connected by an edge to get from one vertex to the next vertex. And we're going to write this path as a list of vertices. So we can find 3 different paths on the graph. So let's say we're finding a path from A to B. You could simply go from A to B. That's a path. A to B or A to B, doesn't matter. Or we could go A to D to B. So A, D, B. Or we could go A, C, E, A, B. Now notice I went back to A before I went to B. That's totally legal. You can repeat a vertex. The only rule is you can't repeat an edge. You can't go over the same edge twice. So if we look at this, A to C, C to E, E to A, and A to B. So we didn't repeat an edge, so that is a legal path. Next we have circuits. Circuits are a special type of path. These are paths that begin and end at the same vertex. So one circuit on this graph would be A to B, B to D, and then D back to A. So we have a path, and it started and stopped in the same place. So that's called a circuit. So if we have an Euler path, Euler means that you use each edge exactly once, and path means you don't necessarily have to start and stop in the same place. So if you follow the numbered edges 1, 2, 3, 4, 5, 6, 7, 8, 9, you notice that you went to each edge exactly once, started at A, finished at G. Now I'm not a huge fan of numbering the graph, and you'll find out in the next section exactly why I'm not a big fan of this. So if I were to ever want to write out this Euler path, I would write out that we went from A to B, and from B to D, then we went D to F, F to E, E to B, B to C, C to D, D to E, and E to G. I would just write it out as a series of letters, just like the definition asks you to do. So in this case, we have an Euler circuit. We used each edge exactly once, and we started and stopped in the same place. So this is the same graph as we had before. The only difference is G goes back to A to complete the circuit. So a circuit starts and stops in the same place, and it is still a path. Euler circuit, you use each edge exactly once. So if we have a connected graph says that you can pick any two vertices on a graph, and you can get from one vertex to the other. There's no gap in the graph. Disconnected means that there's somewhere or some two vertices that you cannot go from one vertex to the other. An edge that when you remove it, the graph goes from being connected to disconnected is called a bridge. So looking at examples, connected graph. This graph is connected because I can get from any point to any other point on this graph just by following the dots or following the edges along. This is not connected because my graph is actually in two parts. So I can't get from C to H. There's no connecting edge. There's no path that can take me from C to H. So we're looking for the bridges here. So bridges means that I can take out an edge and the graph becomes disconnected. If I take out AB, the graph is not disconnected. The graph is still in one piece. Same thing if I take out BC. The three edges that I cannot take out and the graph remain connected are D to E, because E would be separate from the rest of the graph. I could not take out DF because that would leave F and G as a separate part. And I can't take away FG. FG is also a bridge because that will disconnect G from the rest of the graph.